Welcome to this explainer. Today, we're diving right into the invisible infrastructure that literally powers our daily lives. I mean, we depend on electricity for just about everything, right? But the actual journey it takes to get to us, well, it's an engineering marvel that rarely gets the spotlight it deserves. So think about this for a second. How exactly does power reliably travel from a massive generating station directly to your living room? It's something we kind of just take for granted every single time we flip a switch or plug in a phone. But making absolutely sure that power is there exactly when you demand it, that requires some incredibly thoughtful design. Let's unpack exactly how that works. Here is our roadmap for today. We'll start with the building blocks of distribution, move on to the radial distribution system, then the ring main system, and finally wrap up with the interconnected distribution grid.
All right, part 1, the building blocks of distribution.
First step in our toolkit, we've got the busbar. You can essentially think of this as the grand central station of electrical power. A busbar is a highly conductive metallic strip, or sometimes a solid bar, typically made of copper or aluminum. It acts as the central electrical connection point. Its entire job is to consolidate power from incoming sources and then distribute it out to outgoing circuits. And because it acts as this absolutely critical common node where everything meets up, the voltage remains practically constant across the whole thing. Now, the second essential component here is the feeder. This is a primary, high-voltage conductor that carries power from a station straight to the distribution network. But here's the absolute most important thing to remember. There are 0 direct tap-offs made from a feeder to serve individual consumers. No way. You literally cannot just wire your toaster directly into a feeder. And because there are no tap-offs drawing power away along the route, the current stays strictly constant throughout its entire length. This lets engineers dictate the feeder's design primarily by its current carrying capacity. When we put these two side by side, their distinct roles really jump out at you. The busbar is your common node, right? Its defining trait is that the voltage remains practically constant. The feeder, on the other hand, is your direct transport line, so its defining trait is that the current remains constant from end to end. So you've got voltage management on one side, current transport on the other. Together, these two are the absolute bedrock of our entire power distribution system.
Moving on to part 2, the radial distribution system.
Okay, so in a radial distribution system, separate feeders radiate outwards from a single substation, supplying power to distributors at one end only. Picture the branches of a tree. The substation is that thick trunk right at the center, and power flows outward in just one single direction. It splits off into smaller and smaller branches to reach individual neighborhoods and homes. It's incredibly straightforward. Now, the big catch here is that while this tree-like setup is for sure the simplest and most economical system to build, well, it comes with some pretty steep drawbacks. Because power flows in only one direction, its reliability is exceptionally low. Think about that tree analogy again. If a storm hits and snaps a main branch, every single twig and leaf further down is totally cut off. A single fault on a feeder means an instant power outage for all consumers down the line. Plus, if you happen to live at the very farthest edges of this system, you're going to experience some significant voltage drops whenever the network is under heavy load. That brings us to part 3, the ring main system. To fix those massive flaws in the radial network, grid topology evolved into the ring main system. This brilliant design connects the primaries of the distribution transformers in a closed loop. So the circuit literally starts from the substation busbars, loops completely around the geographical area it serves, and comes right back to those exact same busbars. And because it's a closed loop, power can flow in 2 directions. If a fault happens somewhere on the line, engineers can just isolate that specific broken section, and consumers get their power fed from the alternate direction, almost like magic. Plus, all those annoying voltage fluctuations at the consumer end are greatly reduced compared to the old radial setup. Which leads us to the grand finale, part 4, the interconnected distribution grid. So an interconnected system basically takes the concept of the ring main and completely supercharges it. This happens when a ring main system is energized by 2 or more distinct substations. We are talking about the absolute highest level of reliability here. By hooking up multiple substations together, even if one entire substation catastrophically fails, the others in the network just step right up and maintain the power supply seamlessly. It also massively boosts the system's ability to handle sudden peak loads since it can pull power from multiple sources at the exact same time. The trade-off, though? Managing all of this requires some fascinatingly complex protective relaying to isolate faults without accidentally tripping the whole interconnected grid. Let's pull all of this together. Looking at this evolutionary journey side by side really locks in how we trade complexity for total reliability.
We started with the radial system. Power flows in a single direction, super low reliability because of that single point of failure, but hey, it's cheap and simple. Then we stepped up to the ring main system. Power flows in two directions, giving us high reliability through fault isolation with a medium level of complexity. And finally, the interconnected system, multi-directional flow, delivering the absolute highest reliability that can even survive a total substation failure. But, as you'd expect, it demands the absolute highest level of complexity to keep it all running safely.
Understanding this invisible architecture really changes how you look at the world. Those poles and wires outside aren't just random lines. They're part of a meticulously designed living organism. So I'll leave you with this. The next time the power flickers or goes out in your neighborhood, ask yourself, are you sitting out on a vulnerable radial branch, or are you safely tucked into a highly resilient interconnected grid? Thanks so much for joining me for this explainer. Keep questioning how the world works around you, and I'll catch you next time.